When investigating matter or chemistry, the first lesson should be a lesson in safety. And I always like to start by advising elementary teachers to get a lab coat. Why a lab coat? Well, as soon as you put a lab coat on, right away you feel like a science teacher. You have that confidence. Try it and you'll see what I mean. Also, the students will get to see you in the role model of a scientist, as a science teacher doing scientific experiments. And of course, the lab coat protects your clothes. Now, you want to talk to the students about certain safety tips, things that they should and should not do, things like tasting, touching, smelling, mixing unknown chemicals. And one of the most hazardous things in the elementary classroom is an unauthorized experiment. No matter how insignificant, just burning a pencil I consider an unauthorized experiment and has to be discouraged. Now, I like to start out my very first day in my chemistry unit talking about safety and showing them this unauthorized experiment. We're using a chemical that I'm just going to call mystery powder, but for you it's called potassium chlorate, and the chemical formula is KClO3. It's a compound of potassium, chlorine, and oxygen. And you start by reading the warning label, and it talks about all kinds of things. Don't let it come in contact with skin and clothing, and if it does, wash it immediately, and that's what you should do if it happens to you. Now, you want to say to your students, it says not to let this come in contact with anything organic. And then you can go ahead and discuss what the word organic means, things that were living or are still alive, and get these ideas across. You're teaching them new words, new science words. And then you say, well, what can we let it come in contact with? How about this aluminum spoon? Is this organic or not? And most of them will say it's okay to touch it with the spoon. So you've got to take a 1/4 teaspoon of it, and you've got to put it in this glass test tube. Very carefully drop it in and let it sit in there. And then you're going to want to heat it up. But before you heat it up, we have to stress safety once again, so we have to have safety goggles, and you should have at least 2 pair of these in your class, one for you and one for an assistant. So you want to show them that you too can practice safety, and talk to them about the usefulness of safety goggles as far as doing other things too, like mowing your lawn or just changing the oil on your car. Then we want to go ahead and light this burner, and we want to heat this chemical up. Make sure you get all your other chemical out of the way. Heat it up until it melts. Now, we're talking about a normal experiment where someone is melting this chemical down into a liquid. As you can see, it melts to a liquid very quickly, and you want to make sure that all the little powder particles are turned to a liquid before you proceed with this experiment. You might also want to talk about pointing the test tube away from other people and away from yourself whenever you're heating it. And incidentally, this torch is a real handy item, and you can get it at a hardware store. Every school should have at least one of these. You'd be surprised the number of science experiments you can do with a little hot torch like this. Okay, now let's get on with this unauthorized experiment. Here's Johnny in the back of the room, and he knows he's not supposed to let anything organic come in contact with this chemical. So he's sneaking around, and he's going to pull a little trick. He's going to stick a popsicle stick in there. And I'm going to use 2 wood splints instead of a popsicle stick. You can get these at a science supply house, or you can just try using a popsicle stick. And Johnny back there is going to drop these wood splints in, do an unauthorized experiment. Well, watch what happens. Now, believe it or not, this is really a very safe experiment. I've done it many times myself without any problems. In fact, you can clean the test tube with a brush in cold water once it's cooled down. Now, the lesson here is don't do any unauthorized experiments, or they could backfire with the most dramatic results. You might want to bring out the idea of chemical changes. We've just observed one, and this is one of the things your students will be studying later on in the course, where 2 chemicals react and in this case give off a vast amount of heat and light. Regardless of where you go from here, this is definitely a good opener for any unit on chemistry. Now we need to get on with chemistry, and the best place to start is with the atom. Your students should understand that there's 3 main particles in an atom: the proton, the neutron, and the electron. And they should understand that the proton and the neutron are in the nucleus, or the central part of the atom, and the electron orbits around the outside. There's also an electrical charge associated with these particles. The protons, as the word sounds, are positive or plus. The neutrons are neutral. And the electrons are the minus charged particles, just like the plus and minus of a battery. And you should also note that you have to have the same number of minuses as pluses so that the atom balances out and there's no net charge on it. So if you have 15 protons, you have to have 15 electrons to cancel out the charge. Now, how do we tell how many protons and how many neutrons and how many electrons are in a particular atom? Well, now we have to refer to that table, the periodic table. Let's take carbon as an example. The top number in the periodic table is a 6. That's carbon's atomic number. And that's exactly what it means, the number of protons in one carbon atom. So if you have 6 protons, or 6 pluses, you must also have 6 electrons to cancel them out. So we know that we have 6 protons and 6 electrons in a carbon atom. The next question is, how many neutrons do we have? Well, using the bottom number, we can figure that out. The first thing you have to do, and that's called the atomic weight, is round it off. And in carbon's case, it rounds off to 12. 12 is the number of protons plus neutrons added together. If we know the protons are 6, then we got to go 6 plus what makes 12? Well, that's pretty easy to figure out. In some cases, it's not always the same number. Aluminum, for example, you round off the atomic weight, it comes out to be 27, and the atomic number is 13. Therefore, it's got 13 protons and, of course, 13 electrons, but it has 27 minus 13, or 14 neutrons. As we look at the periodic table, we realize that chemistry is really also a foreign language. We not only have to learn these new words like carbon and hydrogen and helium, but we also have to learn and understand what the correct symbol is for the particular element. Now, of the 105 symbols and elements in the periodic table, there's really only a small percentage, like 25 or so, that are of any great importance. And here's the 25 that I would choose. An element is one of 3 general categories in which all matter can be classified. And an element cannot be broken down into any simpler substance by ordinary chemical means, which is very important. Because in contrast to an element, there's the compound and the mixture, and they can both be broken down into elements. Now, a compound is a combination of 2 or more elements that are bound together, and they're bound electrically by the electrical charges in the atom. And they're usually in certain proportions, certain amounts of one element to certain amounts of another element. And an interesting thing about compounds is that the properties of the compound are usually different than the properties of the elements that make them up. For example, sodium is a very highly reactive metal. If you put a very small amount in water, it will violently explode. And chlorine is a very poisonous green gas, and if you breathed any, inhaled any, you'd probably die. But when you mix the two together, you make a compound called sodium chloride, which is ordinary table salt, and we eat it every day. The third and final category, the mixture, is different from the compound in that it doesn't have a certain proportion of elements in it. It can vary. You can have so much dirt and so much water. You can throw more dirt in if you want, and you can mix 20 apples and 30 oranges, or 30 apples and 20 oranges, and you still have a mixture, varying proportions. And the properties of the mixtures is a combination of the properties of the elements that make it up. For example, it'll taste like water and it'll taste like dirt. It won't be a new compound, and it won't have its own properties. It'll have a combination of the properties that make it up. Now let's do an experiment so the students can see the difference between a mixture and a solution. If you were asked to name the most common piece of scientific equipment, what would you say? Well, I would presume that most of you would probably say test tube because everybody associates test tube with science. So why not use test tubes in your class? They're inexpensive, they're fun, and the students really feel like they're doing science when they're working with these. Now, you probably want to get a standard size, and they come in many different sizes. This particular standard size is 20 millimeters across the top, that's the diameter, and the length is 150 millimeters. And it holds about 35 milliliters of liquid. Okay? And when you get the test tube rack to hold the test tubes, you want to make sure that it'll hold the 20 millimeter test tubes. And this one holds 6 test tubes. It's a good size. Also, make sure you have a test tube brush, a test tube cleaner for cleaning them out. And another good idea is a number of test tube clamps so the students can lift them and carry them around. Now tell me this doesn't feel like you're doing science. Now that you've got your test tubes, you're ready to do an experiment. What we're going to do is see how easy we can separate a mixture of cornstarch and water and a mixture or a solution of sugar and water. Now you might first want to start out this experiment by asking your students to hypothetically separate some mixtures, like how would you separate big rocks from little rocks, or how would you separate salt from sand, or think about iron filings and pieces of wood. There's many different kinds, and you can present those as a beginning. Then you want to talk about indicators. What is an indicator? Because we're going to be using indicators in this experiment. Well, I like to express the idea of an indicator is similar to a street light, a signal light. When it's red, it's telling you by the red color to stop. And when it's green, it's telling you by the green color to go. So an indicator is really a chemical that tells you something by changing colors. And we're using 2 indicators in this activity. One indicator is iodine, and you can get it at a science supply house or at your local pharmacy. One of the interesting things about iodine is that it's normally a reddish rust color, and when it comes in contact with starch, it changes color to indicate the presence of starch. You can try it on pieces of white bread or pieces of potato, or even in a cornstarch solution. Now I've made up the cornstarch solution by using about 2 cups of water and 1/4 teaspoon of cornstarch. And you want to make sure it's stirred up real good just before you use it, because the cornstarch will slowly settle out. I've got 2 test tubes of cornstarch. First we want to check test tube number 1 to see what the effect of iodine as the indicator does in the presence of starch. So we'll take about 1/2 eyedropper of iodine and squirt it in. Remember to remind your students that iodine is very poisonous and that it stains clothes and fingers. Watch what happens when it comes in contact with the starch. You see it changes color and it turns to this purpley black color. It's telling us that starch is present in this test tube. As you let it sit, it develops even more and turns an even darker color. Now we want to try and get the cornstarch or the starch out of this second test tube that we filled up from our beaker. The way we're going to try and do it is filter it. So you're going to need some filter paper and you're going to need a funnel. You can get a regular Melita coffee filter and inscribe a 7-centimeter circle on it and cut it out, and you'll end up with 2 pieces of filter paper at once. This incidentally is a number 6 filter. Now once you've cut out the filter papers, how do you properly fold it so you can use it in your funnel? Well, first you want to fold it in half once. Then you want to fold it in half again. You have a little triangular shape. Then you want to separate it so that there's 3 layers on one side and 1 layer on the other, so it opens up into a cone. And then you want to put it in your funnel. Wet the funnel first. It keeps the filter paper in place. And make sure that your students don't poke the filter paper down with a pencil, but just press it in with their fingers. Now we want to filter this starch solution, the cornstarch, and we're going to filter it from test tube 2 into test tube 3. So you may want to have some written directions when you do this one. Pouring it in here, we're getting a filtrate to come out down at the bottom. Once this is done, we want to test this filtered solution to see if it still has the starch in it. And we'll test it with 1/2 eyedropper of iodine. Right away we notice that it didn't turn the black-purple color like we might have expected. So we find out that we can effectively separate the starch from the water by simple means of filtration. Now we want to go on and try the same technique, but this time on a sugar-water solution. And we can't use iodine for the indicator here. We have to use something else. I found one of the best indicators, something you can get in the pharmacy. It's behind the counter, so you have to ask your pharmacist for it, but you don't need a prescription. It's called test tape, and it comes in a dispenser. It's very easy to use, and it's used for determining the amount of glucose in urine, and it's used by diabetics. What you do is you tear off a little strip of this stuff, and you can get about enough test tape in one of these dispensers for 100 separate experiments. And you test it by dipping it in what you think is a sugar solution. It has to be glucose sugar now. I'll talk about that in a second. And then you wait for a minute for this particular piece of chemically treated paper to develop, and then you match up the color. So it's kind of a quantitative measurement as compared to qualitative. It tells you the quantity of the sugar that's present in percentages. And if you are working with one particular class, you may want to use the upper scale that says 0, 1 plus, 2 pluses, 3 pluses, and 4 pluses. Or if you're talking about percentages and you want to work that into your program, we have 1/10 of a percent, 1/4 of a percent, 1/2 a percent, and 2% or more if it turns the real dark green color. So this particular concentration looks like it's somewhere between 1/10 of a percent and 1/4 of a percent. Now, how did I make this solution? Well, here I'm using corn syrup. It has to be glucose. That's the kind of sugar that's in our blood. And I took, I think, about 1/2 teaspoon of corn syrup and mixed it in a quart of water and mixed it all up. You can experiment on your own to find the particular proportion you like, but that's a good place to start. If you can't find corn syrup, you can use pancake syrup or anything that's got corn syrup in it. Now, back to this experiment. We want to see if we can separate the sugar from this water. So we want to do the same thing. We want to get a fresh piece of filter paper, pour it into the filter paper, collect the filtrate, test it once again after you first tested it, test it a second time with a test strip to see if the sugar is there. Your students will find in this experiment that the sugar goes right through the filter paper. So you want to ask them why. And the idea that you want them to come up with is that these sugar molecules are attached to the water, and wherever the water goes, it takes the sugar with it. It's a solution. And if you tasted the top part of the sugar water, it would taste sweet, just as sweet as the bottom part. It's evenly dispersed throughout. But it's still a mixture. You can have a lot of sugar in here, or you can have a little sugar in here. In fact, with this particular mixture that we mixed up, you can hardly taste the corn syrup in this water. The important part about all this is that we're doing experiments. The students are learning the experimental process. And as a result of doing one experiment, they're finding more questions that they need to have answered about other things. For example, why does this indicator only detect glucose? And what are some other types of sugar? And why are they different? Well, this is a perfect lead-in to understanding compounds. Sugar is a compound made of 3 elements. And the way I have my students remember them is I bring in a box of C&H sugar. This is how you remember it. Carbon and hydrogen are 2 of the elements in sugar. The other one, the third one, is this oval, this O, carbon, hydrogen, and oxygen. That's the formula for sugar. Now the question is, what is the ratio of these elements in the sugar molecule? Well, cane sugar or beet sugar is called sucrose, and that's the sugar we're most familiar with, and the chemical formula for that is C12, that's 12 carbons, H22, 22 hydrogens, O11, 11 oxygens. The kind of sugar that we just used in the last experiment is glucose. That is called grape sugar, or even blood sugar sometimes, because our body takes sucrose and breaks it down from this more complex sugar to a simpler sugar. The chemical formula for glucose is C6H12O6, and you can see right away that it's a simpler molecule than this one. Now there's other kinds of sugar compounds too. There's lactose or milk sugar. There's fructose, which is the sweetest sugar there is. And if you can get samples of these, bring them in, let your students taste them, they'll get a better understanding of different types of compounds. They're very closely related. They're all carbon, hydrogen, and oxygen compounds, and the ratio or the proportions are very close, so they're considered in the sugar family. It should be noted here that scientists group compounds according to their chemical formulas. Some examples are the alcohols, the salts, the acids, and the bases. Now, How do these elements come together to form compounds, and why do only some elements form compounds with other elements? Well, if you think back and you remember that atoms are made of protons and neutrons in the nucleus and electrons spinning around the outside, and the electrons have the minus charge. Now, if these electrons either get more electrons than they're supposed to have, or they lose some of their electrons, then they're going to have a net charge on the atom. For example, if it has 8 electrons and 8 protons, it's balanced. But if it gets 2 more electrons, then it's going to have 2 more minuses than it has pluses. So it's going to have a -2 charge on it. That's what happens to oxygen. And you can have your students make little cutouts like this to help understand the compounds. You can use construction paper or you can use poster board. Oxygen, made like this, will have 2 extra electrons, and I like to use indentations to show the minus side. So we have a -1 here and a -1 here. Hydrogen has a tendency to lose 1 electron, so it ends out with a +1 charge. So it's +1. Oxygen is -2. Now we're talking about pluses and minuses and how they come together. If this was -2 and this was +1, how many of these would it take to lock into this to make a compound? Well, it would take 2 hydrogens to go to 1 oxygen. So we have a +1 going in here and a +1 going in here, and we now end out with a compound, H2O, which is water. When the Hindenburg, the big blimp, blew up, it was hydrogen in the blimp combining with the oxygen in the air, burning with incredible intensity and making water. Let's look at some more compounds down here. We have sodium, and sodium also has a tendency to get a +1 charge on it. Chlorine, on the other hand, has a tendency to get a -1. And if you look at that periodic chart, it's interesting to note that the ones on the left-hand side are the ones that get the plus charges, and the ones on the right-hand side are the ones that get the minus charges. And they're really lined up according to the charges they get if you look closer. What would happen here? How many sodiums, which is +1, would combine with chlorine, which is -1? Well, it looks like 1 and 1, and they just go right in and lock together. Sodium chloride. And we always read a chemical compound by the one that's plus first. So sodium has the plus charge, so we call it sodium chloride, not chloride sodium in that order. This would be dihydrogen oxide if you didn't want to call it water. 2 hydrogens and 1 oxygen. What else can we make out of this? Well, it looks like we could put the sodiums in with the oxygen because they're +1, and they would just happen to fit right in here. And we would get Na2O, 2 Nas and 1 O, 2 sodiums and an oxygen. That would be called sodium oxide. Looks like we could also get this one over here. How about this? HCl. What would you call that? Hydrogen chloride. Or it's also called hydrochloric acid. This compound is used in swimming pools to disinfect, kill bacteria, and it's also found in our stomach where it aids in digestion. The point we're getting across with this activity is that elements gain or lose electrons, and they get charged up, and they're not called atoms anymore. When they get charged up, they're called ions. And these ions combine with other ions. The plus ions combine with the minus ions to form compounds. They combine in the right proportions, the correct proportions for the jigsaw puzzle to come together. If your students just start to understand this, you will have taken a great step into getting them to understand chemistry. There's one set of elements that do not gain or lose electrons, the ones in the far right-hand side of the chart. These are called the inert elements: helium, neon, krypton, argon, and so forth. They're perfectly happy the way they are. There's no tendency for them to gain or lose electrons, so they don't get charged up. As a result of that, they don't combine with any other elements on the chart. While we're on the topic of compounds, there's 2 major families of compounds that we should investigate: the acids and the bases. And how is one different from the other? Well, let's go back to this model with the construction paper cutouts. First, let's look to this one on the left, hydrogen chloride or hydrochloric acid. Why is it an acid? Well, remember that hydrogen has a +1 charge, and when HCl is put in water, it comes apart, and we start to get all these little hydrogens swimming around inside the liquid. The more hydrogens that are free with the little +1 charge on them swimming around in this liquid, the stronger the acid will be. Every acid has this hydrogen ion in it. And you can always tell an acid because the chemical formula always starts with an H. HCl is a perfect example, hydrochloric acid. Sulfuric acid is H2SO4. Nitric acid is HNO3. So that determines what an acid is. So what is a base? Well, think of this. If an acid is +1 ion swimming around, and a base is opposite of an acid, what do you think the little ions are that are in the base? -1. You're right. And in the base, the way we get our -1, this particular base is called sodium hydroxide, is when this dissociates, the sodium comes apart and it leaves oxygen and hydrogen. Now remember that the hydrogen has a +1 charge and the oxygen has a -2 charge. So when those two are combined and locked together, you get this hydroxide, this OH. And since it's -2 and +1, we end up with that -1 charge. And the more little OHs that are swimming around in this liquid, the stronger the base will be, like lye and oven cleaner, ammonia, all very strong bases. Now what do you think will happen when we take the -1 and we mix it with the +1? All my students always say it's going to totally explode and wipe out the world. Well, not really. What happens is the hydrogen, which is a +1, comes across over here and fits right in here with this OH, this hydroxide, and forms H2O, water. Incidentally, H2O can be written as HOH. Looks like an acid because it starts with an H, but it looks like a base because it ends with an OH, so it's neutral. It's not really an acid or a base. And incidentally, all bases end with an OH. That's one way you can identify a base, because it has that OH on the end of it, and it's always called a hydroxide. What else is left in this reaction? Well, we've neutralized those two, and we have Na and we have Cl left here, so they'll come together over here and form NaCl. This is common ordinary table salt. Now it may not be table salt. It may be some other kind of salt. It depends on the acid and the base that you start with. For example, we could have started with KOH, potassium hydroxide, over here, and HCl, and we would have gotten KCl as the example here. Let's now take a look at some indicators we can use to detect the relative amounts of the hydrogen ions in the acid and the hydroxide ions in the bases. We measure the relative strength of an acid or a base using a scale called pH. This scale runs from 1 to 14, with the number 7 in the middle representing the pH value of a neutral solution. Now the question is, which numbers are the acids and which numbers are the bases? The way I remember it is that A comes before B in the alphabet and 1 comes before 14. So the low end represents the strongest acids and the high end represents the strongest bases. As we approach 7 from either side, we find the weak acids on the 6 side and the weak bases on the 8 side. Now, we want to measure actual values of acids and bases, and one of the best indicators you can use is this stuff right here. It's called Accutint, and it's a pH paper, and it's specially treated, and it changes different colors, and you have all the color range here. This is a wide range pH paper, and it goes from 1 to 12 in increments of 1. Now, how do we use this pH paper? Well, pull out the size sample you need, put your thumb against the plastic backing and tear it off. If you don't put your thumb against the backing, you may lose the paper inside the dispenser and have to pry it open to get it back out. Then test the sample. This sample over here tests out to have a pH of about 2, and it's vinegar. And if you're going to have your students walking around with these, make sure they have some place to dispose of these used pH papers in. I give them a little Dixie cup, because otherwise you'll end up having all the pH paper stuck in your samples. This sample over here on the other side tests out to be 10 or 11, so it appears to be a very strong base. And what it is ammonia, NH4OH, ammonia hydroxide. This is the most versatile and easy to use indicator for finding acids and bases. What can you do with it? Well, you can give your students mystery liquids, number 1, number 2, number 3, maybe 10 different liquids, and if they understand pH, let them go around and record the actual pH value of each liquid, and then decide whether it's a strong acid like a 1 or a 2, or it's a weak acid like a 6 or a 5, or maybe a weak base like a 8 or a 9, or a strong base maybe up to 12 or 13. This pH paper, by the way, is from 1 to 12. And you can get it in vials too. But make sure when you order pH paper that you get the wide range pH paper for the most versatility. Now, another thing you can do with this is you can give them like 10 or 15 different foods and different household chemicals and have them go around and find the pH of the chemicals. They realize right away that there's some very dangerous chemicals on the market like Drano or oven cleaner, and that's why you're supposed to wear gloves if you ever come in contact with it. Very strong bases. Some of the foods we eat, like pickle juice, for example, and I've got some right here. What would you expect it to be, an acid or a base? Well, as we dip it in here, we see right away that it comes out to be about a 2. So it's a acid. And you can go on to all these different foods like egg whites and milk. You could even crush up a Tums or Rolaids tablet, an antacid tablet. That must be a base. And put a little water with it and let your students test that. Put little signs by each sample and say what it is, and then let them go around with their answer sheet and fill in the pH value and then decide whether it's an acid or a base. Now here's another indicator that works very well, but it's a narrow range indicator, and it's right around 7. So it'll tell us if something is either on one side of 7 or the other side of 7. And that indicator is called bromothymol blue. You can find this chemical in drugstores under pool supplies or in a pet store because it's used to measure the pH of water in an aquarium. Or you can order it through a science supply catalog. One of the things I like to test with my bromothymol blue is tap water, but before we do that, let's test some distilled water. That's this glass right here. We would expect that distilled water would have a pH of 7.0, and put a few drops of bromothymol blue, swirl it around, you're going to see that it makes a nice color. Then you need the color chart to compare it to. What is the pH of this particular water? Well, it looks like it's right around here, 6.8, 7.0, so it lines right up with neutral, and that's what we would expect. Well, what would my tap water be? Well, let's try my tap water here. Put a few drops of bromothymol blue in here in the tap water, swirl it around, and look at the color difference. Here's the distilled water, here's the tap water. To think I'm drinking this stuff. Now, is this acidic or is it basic? Well, it's on one side or the other, so we need to look at our chart again, and it looks like it's over in here with a pH of 7.4. So my tap water is slightly basic. Now, this is probably caused by minerals that are dissolved in the water. Now, here's an interesting demonstration. We know that when we breathe air out, there's a certain amount of CO2 that we breathe out, carbon dioxide. And another thing about carbon dioxide is when it combines with water, it forms a very weak acid, and this is one of the constituents in acid rain. Now, if we blew our breath through this water, we would form a weak acid, and the weak acid would neutralize some of the weak base. So what do you think would happen as I bubbled my breath through this glass of water? Well, watch this. You can see that we've effectively changed the pH of our tap water just by blowing our breath through it. It's that mild acid that's neutralized the base. Now let's go on with this idea and ask another question. Here's some tonic water. You could use 7-Up too. Tonic water we know has carbonated water in with it. What will happen when we put our bromothymol blue in the tonic water? Watch this. The pH of the tonic water is quite low. It's coming down to a yellowy color, and this is the lower end of the pH scale for our bromothymol blue, and it looks like the pH of this tonic water is about 6.2. Now there's many things we can do with bromothymol blue. We could test our tap water every day and record the pH value and see how much it varies. We could go out and test swimming pools and see what the pH is of different pools. Or we could go out to lakes and ponds and check the local value of the pH of that particular water. Remember that bromothymol blue is a very narrow range indicator, and it only goes from about 6.2 to about 7.4. Now there's one more indicator I have to show you. It's called phenolphthalein. And phenolphthalein only changes color, it only indicates bases. It's normally a clear color like this, but look at the beautiful color it makes when it's dropped in a base. Now let's try this neutralization reaction. Let's take part of our ammonia that's sitting with the phenolphthalein in it, and let's pour some vinegar, some acid with it. What do you think will happen when we mix the acid in the base? It neutralizes the base and the phenolphthalein disappears. What would happen if we poured more base in here, mixed some more base in here? Well, look at this. The phenolphthalein reappears because we're going back and forth from acid to base. And this is really an interesting little activity. Your students will get a kick out of it, and you'll be explaining the idea of indicators and acids and bases. There are many different types of indicators that are used to measure the pH of acids and bases. The ones I've shown you here are my three favorites: bromothymol blue, phenolphthalein, and the wide range litmus papers. You may wish to try some of the others on your own, but you have to remember that every indicator has a specific pH range in which it works.